Now we're going to talk about something called the Doppler's effect. What is a Doppler effect? If you have a stationary source, like for example, I am a stationary source of noise right now, and you are both stationary listeners, this is what you would see. Sound starting at a certain point and then emanating outwards as it goes. However, what happens if one of the two, either the source or the observer, that's what I'm calling, starts to move? Have you heard that before? What does that sound like? Listen to it again. Yes. It sounds like a train passing by you. We've all heard that before, or some form of it, like a police car, an ambulance, a train, something passing by you. And you instantly know, without me telling you or without me showing you, that that is some kind of a vehicle that is passing by you, right? That, in terms of physics, is called the Doppler's effect. And this is what's going on. I want you to notice very carefully the dot moving. Do you think it's getting faster or slower? Just the dot, just focus on the dot. Is it getting faster, slower, or staying the same speed? Staying the same speed? Good. Now I want you to observe the whole picture. Remember the stationary sound? It looks like this. Yes? But then what happens if the sound starts to move? What is actually going on is that the waves of sound are actually bunching in front of the moving vehicle. So when it is approaching you, more of these waves are reaching you, the faster that thing is going. And when it goes away from you, there's a quick, like a whoop kind of thing, and then it starts to go away. Notice what happens when it crosses the ear. What is the ear experiencing now? Larger wavelength, right? Going away, so a lower pitch. Again, we'll talk about it a little bit more. So this situation is when the observer moves towards a stationary source. He's reaching into the waves on one end, and he's going away from the waves on the other end. On the other hand, if the source is moving towards the observer with a constant speed, that's what he's observing. So what all is going on? Notice, if you are the observer standing here, can you tell the instant when this car passed you by? Okay, listen to it one more time. Tell me when. Everybody, tell me when it's passing you. Okay? Can everybody tell that? Because when it's right in path of you, that's the actual frequency. Before that, it was a high pitch, getting higher, and suddenly it changed and it became lower, and it goes away, right? So in terms of physics, look at this bunching. Yeah? Whereas look at this. High-pitched noise when it's coming towards you, low pitch when it's going away from you. And there is a reason for this. And the reason is very simple. It goes back to our standard formula that we have been talking about. Speed equals distance over time. Or, for the case of a wave, lambda f. Now, as the observer or the source moves, what do we know? The distance between them changes. However, if we keep the speed of our source constant, the speed of the wave will remain constant. Which means, in order to keep the speed the same, if the distance is changing, something else must change in order for the speed to remain constant. So speed equals distance over time. We know that time is the same as, distance is the same as lambda, time is t. So we can also write it as lambda f. In order to keep the speed the same, frequency must change in this formula, because v cannot change. That's basic math. So for example, think about it this way. There are two boxes on this side, and there is one box on this side plus one box on this side. If this box can have 10 apples, and this box has 2 apples, how many apples must this box have to create 10 apples? 8, right? That's my only option. But what if I put 5 apples in this case? But this box can only, like the 2 boxes can only have 10 apples in total. What must happen to this box? How many apples must now there be in this box for this equation to balance, right? 5. Is that true? That's exactly what's going on here. This speed cannot change. So if in order to keep, and if lambda changes, frequency must change. If the distance cannot change, frequency must change. So remember this. When the source and observer move towards each other, the distance between them is getting smaller and smaller, which means in the same time interval, the same number of waves must fit in there. The only possibility is that the frequency of the incoming wave has to go up. Okay, or the apparent frequency must go up. On the other hand, if the objects and the distances are going away from each other, that means the distance between them is getting larger and larger and larger and larger. That means the frequency must go down, which means the pitch should also go down. And that is what you were observing here. Listen for it again. Right? Okay, I'm going to make you hear that one more time. Notice it going up. Does that make sense? And it will slowly go up, and then it will slowly come down. But that instant of time when you know that it's passing you by is when it transitions from going up to going down. And that's called the Doppler's effect.